Let's derive Euler's crippling load for a column fixed at one end and hinged at the other. We start with a straight vertical column of length L, perfectly fixed at its base. The top of the column is supported by a hinge, which allows it to rotate but not move horizontally. When an axial compressive load P reaches the critical buckling limit, the column deflects sideways. Because the fixed base resists rotation, horizontal reaction forces H develop at both supports to maintain equilibrium. To analyze the internal forces, we take a cross-section at a distance x from the fixed base. The internal bending moment at this section is calculated by summing the moments from the reaction forces above it. This moment consists of the horizontal reaction H times its lever arm, minus the load P times the lateral deflection Y. Using the Euler-Bernoulli beam theory, we equate this bending moment to the flexural rigidity, EI, times the second derivative of deflection. We can rearrange this into a standard second-order linear differential equation, substituting k squared for P over EI. The general solution to this differential equation combines a homogeneous part and a particular integral. The sine and cosine terms represent the natural wavy shape of the buckled column. Now we apply boundary conditions. At the fixed base, where x is 0, the lateral deflection is 0. Substituting x equals 0 into our equation gives us our first constant of integration, c1. Also, at the fixed base, the slope of the column must be 0 because it is rigidly held in place. Taking the derivative of our equation and setting it to 0 yields our second constant, c2. Finally, at the hinged top, where x equals L, the deflection is once again constrained to 0. We substitute our constants c1 and c2, along with x equals L, back into the general deflection equation. Assuming the horizontal reaction H is not 0, we divide it out and rearrange the terms to get the characteristic equation, tan of KL equals KL. This is a transcendental equation, which we can solve graphically by plotting y equals x and finding where it intersects the curve of y equals tan x. The first non-zero intersection point occurs at approximately 4.4934 radians. Squaring this value gives us roughly 2 pi squared, leading directly to Euler's crippling load formula. This tells us the critical load is 2 pi squared EI over L squared, meaning the effective length is L divided by the square root of 2.